Hi, and welcome to E3 heat. Heat is just a type of kinetic energy. So, heat is basically a measure of the random kinetic energy in the molecules or atoms of an object. So, if you have water at a low temperature, those water molecules are moving really quite slowly. But if as you heat that temperature up, what you're doing is effectively increasing the average kinetic energy of the water until a point. If we're talking about water, if it started out as liquid water, if it's close to 0 degrees, they're moving very slowly. As you increase that temperature towards 100 degrees, more and more of those atoms have the average kinetic energy to break free of the surface tension and start evaporating and creating steam. It's also interesting to talk about how this is an average. It's an average kinetic energy of the molecules. So some of those molecules are going to have substantially higher than the average, and some of them are going to have substantially lower. And substantially lower is a little bit boring because it means that two water atoms might try and briefly for a second create ice, but then a third atom will come and whack into it and break that bond up, and it'll never form. But it's the reason why at say 20 degrees Celsius over time a cup of water will actually evaporate. It's because of the average kinetic energy. Some of them are going to move faster. And so if you're moving faster and you break free of the surface of that water, you turn into water vapor, there's no going back immediately. Nothing's going to knock you back in there, which is why some water will evaporate well below 100 degrees. At 100 degrees, the average water molecule has enough kinetic energy that it'll start boiling off into the atmosphere. So when we talk about the relationship between energy and heat, we end up with the mathematical equation E is equal to mc delta T. E, and I like to put a little H right there. So EH is heat energy. It's just another type of energy, kind of like potential energy or kinetic energy, if you want to be specific. It's a type of kinetic energy. M is the mass of the object. So the larger the object, the more energy it'll take to increase the heat of that object. If you can imagine a blowtorch as a source of kinetic energy or as a source of thermal energy, and you take it and you point it at a piece of metal. If that piece of metal is very small, it'll heat up quite rapidly. But if that piece of metal is very large, very massive, has a lot of mass, it'll take a while to heat up. I'm going to talk about C in just a second, but I want to talk about delta T first because it's quite straightforward. And this is the change in temperature. Heat energy is in joules. Mass of an object, we measure mass in kilograms. Change in temperature. So the change in temperature in the metric system, we usually use in physics 11 degrees centigrade. The way the degrees centigrade system was imagined is they realized that water froze at a certain temperature and they realized that water boiled at a certain temperature. And so they took a little cylinder full of mercury and they made a mark on it. They stuck the end of it into the frozen water and they made a mark, and then they stuck the end of it into the boiling water and they made another mark, and then they drew 100 marks in between. And that's how we came up with the Celsius system. So there's 100 degrees between the melting point and the boiling point of water. It turns out, though, that that's not necessarily the most scientific way about it. And when we start talking about temperature as related to energy, it would make more sense to have the 0 degrees instead of where some random substance starts to freeze, as when there is no energy. So the system they came up with as the no energy is 0 degrees system is called Kelvin. They still like the size of the measurements of those increments. So 1 degree Celsius, the change in 1 degree Celsius is the change in 1 degree Kelvin. those two are equal, so it doesn't make much difference in what we're going to go through. It's completely interchangeable, degrees Celsius or degrees Kelvin. But degree Kelvin just has a different starting point, and that's just representing what we found out after we'd invented a temperature system and a way of measuring temperature, and that's that energy is directly related to temperature, and so that system should reflect that. So 0 degree Kelvin is when there is no heat energy in an object at all. There is no random motion of the particles. The average kinetic energy is 0. And then we need to talk about C, which is the specific heat capacity. So the specific heat capacity of an object is how much energy it takes to increase the temperature or decrease the temperature. It turns out that different substances take way more or less energy to change the temperature. Let's look at units and then we'll look at this table that I've got below us. So if I was to rearrange this energy equation that I wrote down first, so that it was solved for C, I would get a C is equal to E divided by m delta T. So my units for C must be joules per kilogram degree Celsius. So what C is it's the amount of energy it would take to increase 1 kilogram of the substance by 1 degree Celsius. So if you have a very large specific heat capacity, it's quite hard to change your temperature. If you have a very low specific heat capacity, it means you need a very small amount of energy to change the temperature for any 1 kilogram. And I can write down these units over here for the sake of consistent notes: joules per kilogram degrees Celsius. And you find this out experimentally. There's no real way to calculate it. I can't say water, calculate it. But so what they've constructed is some tables. So I've copy and pasted one here. It's the same one that'll be on your worksheet. So if we're talking about heat, I'll either have to give you a specific heat capacity or you'll have to calculate it. And if you calculate it, you could probably tell me what the substance is as well. It's a lot like the coefficient of friction. They're determined experimentally, and then we will look them up with Google or on tables and figure out what they are. We'll notice that things like aluminum and copper. Aluminum takes 900 joules per kilogram degree Celsius, and copper has a specific heat capacity of 390. And what that means is it takes way less way less energy to increase the temperature of copper, which is why it's frequently used in frying pans, because you can bring it up to temperature really fast with a small amount of energy. Iron or steel, also quite pot-like, also frequently used in pots, is quite close to copper. But copper pots are quite expensive, so iron or steel is a pretty good happy medium. The reason we don't use lead to make pots is because it would melt. Marble, silver, water. Water is the one I'm looking for. And the reason I really talked about some of those other ones is because of water. So water is 4,180 joules. So notice how different that is compared to everything else on this list. With the exception of ice, which is a form of water, it is 4 times more energy to increase a kilogram of water per degree Celsius than anything else on this list. And the relevance of this is because it's really quoted as one of the reasons that you need it on a planet to have life. And also, what we're doing with the planet right now with global warming, it takes a phenomenal amount of energy to increase water's temperature. So when we talk about the oceans being increased in temperature by 3 degrees Celsius, we're talking about this is a sponge that can pick up that energy. But once we put all that energy in, it's going to be really hard to bring it back down as well. But it kind of acts as a damper for all the energy coming in and out of planets. And so if you have a lot of water, your planet should have the ability to keep a consistent temperature, which is quoted as being super important for developing life. Interesting side note. E is equal to mc delta t. This is a four variable equation on its own. It's not really that tricky. I could ask an example question like, um, one, how much energy is needed to warm 7 kilograms of copper by, well, I've already used 7. Let's call it a 14 degrees Celsius. So E is equal to mc delta T. How much energy is what I'm looking for. My mass is 7. I can look up copper. It's right here. The specific heat capacity is 390, and I want to increase that temperature. So the change in temperature is going to be 14 degrees Celsius. E is equal to 7 times 390 times 14. We will pull out a calculator. It'll take a second. There we go. 7 times 390 times 14, and that's going to be equal to 38,200, I think is what it said, joules, which is a lot of energy. And I think those are fairly straightforward. If I'm not doing anything there, then there's no real algebra, and you guys at this point in your academic careers can rearrange a four variable equation in your sleep. So let's look at an example 2. How long will it take a 500 watt kettle to boil 3 liters of water if the water starts at 18 degrees Celsius? How long will it take a 500 watt kettle to boil 3 liters of water if the water starts at 18 degrees Celsius? This is a pretty applicable question. Electric kettles are typically sold by wattage. Big wattage means very strong. Small wattage means not very strong. 500 watts is pretty weak. 2,000 watts would probably be a bit more average. So a couple of things we need to know for this question. Water, by definition, each liter is 1 kilogram. So 3 liters of water is the same as 3 kilograms of water. So that's related to my mass. My temperature starts at 18 degrees Celsius, and I'm looking at a final temperature, if it's boiling, is 100 degrees Celsius. And now I have to look at this 500 watts, and we're asking about how long. So watts is a measure of power, which we will talk more about. But for today, all you need to know is that power is equal to energy over time. We can write that down. P is equal to power, E is equal to energy. T is equal to time. We can scribble some units in if you want. Times in second, energies in joules, powers in watts, which means a watt is 1 joule per second. Which what that 500 watts is telling you is that every second it's adding 500 joules to this kettle. So if power is equal to energy divided by time, then energy is equal to power times time. And I can rearrange this. E is equal to mc delta T to power times time is equal to mc T final minus T initial. Notice how I have two different types of T's here. I've got a capital T and a lowercase t. So if you've been lazy so far and haven't been differentiating between the two or flopping between them, you're going to end up in trouble. Time is usually a lowercase t. Temperature is usually an uppercase T. So we're looking for time. I can divide both sides by P, and I end up with this mct final minus T initial in brackets divided by P is equal to time. My mass is going to be 3 kilograms. The sea of water is 4,180. That's my specific heat capacity. My final temperature is going to be 100. My initial temperature is going to be 18, and it is a 500-watt kettle. We jump over our calculator and do a 3 times 4180 times, open that bracket up, 100 minus 18, close the bracket, divided by 500. 2,056 seconds. Not really a normal unit of measurements, so we could, if we wanted to, divide that by 60 to get minutes, seconds, and we find that my weak 500-watt kettle takes 34 minutes to boil. Do not buy a 500-watt kettle. That's a real calculation. If your kettle says 500 watts, don't get it. Let's look at my next slide. This was a meme I found just the other day. Because kinetic energy can be directly converted into thermal energy, if you were to slap a chicken at 3,325 miles per hour, you would cook it. This was a meme that circulated a couple years ago, and I just came across it appropriately, I think this morning or yesterday. But there's some elements of truth here. You have in your hand, you would have some kinetic energy, and that kinetic energy could 100% be transferred into thermal energy. And then you would increase the temperature of the chicken. I think in reality, you would slap the chicken to smithereens and it would be absolutely destroyed, and would not really increase the temperature, although the average kinetic energy of all these tiny pieces of chicken would be higher. I think it's more realistic to look at something like a waterfall. I can't remember the height of Della Falls on Vancouver Island. What happens if we Google it real quick? There's all your next worksheets. If we look up Della Falls, what do we get to? Longest drop is 179 meters. I think it's higher than that, though. Let's see what Wikipedia says about Della Falls. It's on Vancouver Island. It's just kind of north of Port Alberni. There you go, 60 kilometers, discovery height. The total vertical drop is 440 meters. So let's take a look at what happens to the temperature of Della Falls. Della Falls drops 440 meters. What is the increase in temperature of the falls? So what I'm getting at here is this relates to the previous lesson about conservation of energy. So you have Della Falls, you have water at the top of the falls, which has potential energy. It's up 440 meters. It's going to fall 440 meters. So as that water falls, the potential energy turns into kinetic energy. You have water that's moving with kinetic energy, but then when it hits the pool, all of that falling energy turns into random motion in the water as it mixes around and you get a still pool at the bottom. What you have is you have potential energy that's turned into kinetic energy that has then turned into thermal energy. So if we look at this, we can look at water at the top of the falls and water at the bottom of the falls. So we can look at the sum of the energy at the top versus the sum of the energy at the bottom. So at the top, I have EP and EK potentially. And at the bottom, I'm going to talk about potential energy and kinetic energy. And now we have this heat energy, or maybe just to be consistent, I'll do an EH. I can't remember what's on your formula sheet. It'll either be a capital H or an E with a capital H. So the top of the waterfall, we can ignore the kinetic energy. It's not moving very fast. We imagine a really large pool up there with very little motion. So it's all potential energy. At the bottom of the waterfall, once it's all fallen down and has come to rest in that pool, we're on the ground now, so there's no potential energy. And if we wait until the general masses stop moving, then there's no kinetic energy. And what we have is we've turned that gravitational potential energy all into thermal energy. So this is an interesting claim to make. This says that all waterfalls will increase the temperature of the water as they fall. And some people are going to look at me like I'm crazy right now. Because if this was true, then you'd kind of have a hot spring at the bottom of every fall. So we're going to commit to this line of thought and see what happens. I have an mgh for potential energy is going to be equal to an mc delta T. And we're looking for the increase in temperature, so we don't have to do anything with delta T. Notice I have a mass on both sides, so that'll cancel. And so I have a GH divided by C is equal to delta T. I'm going to have to bop back to look up at the specific heat capacity of water, 4,180. I'm going to scribble this over here so I don't forget it, 4,180. So G is 9.8. My height is 440 meters. I don't need to put those units in there. And my specific heat capacity is 4,180. And that's going to be the increase in temperature. 9. Let's clear the 9.8 times my 440 divided by 4180. 1.03. So the change in temperature is 1.03 degrees Celsius. So I think the moral of this story is, yeah, it is a thing. It is a thing that happens. Conservation of energy is definitely a thing that's been routinely proven in a variety of cases. It's not necessarily wrong, and this isn't a bad lens to look at this through. But the change is 1 degree Celsius isn't going to be easy to measure. It's hardly anything. The difference between 18 and 19 degrees is not much. That energy, also the potential energy, would be spread out into the ground and the rocks around it. So in reality, it would be subtly less than that as well.
Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video. And step number three to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.